Hi everyone. Ooh, that was loud, wasn't it? Hi everyone. I'm here to talk about performance or searching for time. My name is Georg Kullgren and I'm working at Net Insight, a relatively small company with 230 employees. We're located just north of Stockholm in Solna. Our main product line is a number of video switches used mainly for live broadcasts and mostly on the production side, where we have a lot of cameras on site on a big live event and sending streams to a production company. What you see here is our largest switch. It has a 600 gigabit per second backend. And as you may be able to see here, we have 6 slots where you can put different plug-in cards with the different configurations of optical interfaces for communicating over optic fibers. We do everything that you see here. We design the hardware, the chassis, the PCBs. We have multiple FPGAs with custom firmware written with VHDL. We have several CPUs running Linux and, of course, applications in C++. We also have front-end work and we have things in the cloud, so we are full stack for real, if you want. Internally, we use a protocol called DTM to route traffic or transmit traffic to streams. DTM is not like IP, where we look at the headers to send things in the right direction. Instead, we have a frame of a certain size that is divided up into time slots. So if you want to configure a video stream from one point in the network to another point, you allocate a number of time slots to guarantee the bandwidth for this stream. And then the routing is done based only on the slot number to direct it in the right place. So it's more of a configured routing, not a dynamic routing. Wrong direction. I have to learn this one. Here is an extremely simple example of how it works. We have 4 streams coming in, and then they're split. They have different time slots to be transmitted. They have different number of allocated time slots. They have different bandwidths. About a year ago, we were tasked with improving the capacity of this switch. We were supposed to increase it from 600 gigabit per second to 1.2 terabit per second. And this also meant that the internal ports in the switch fabric needed to be increased from 25 to 49 ports. And once we started getting in place, new firmware for the FPGAs, updated the C++ applications, we started to run some measurements. And what you see here is a graph showing the time it takes to reconfigure the switch depending on how many time slots have been affected by the change. And as you can see, for really large changes, it took almost 1.8 seconds for the small switch. With a larger switch, we expected things to get a little bit worse. But maybe not this much worse. Now we're all of a sudden up to almost 3 seconds. And although with a larger switch fabric, of course, there are more calculations needed, but this was a problem for us. We needed to do something. So what to do? The first step is always to get more information. And GNU provides us with a really good tool called perf, where we can look at the execution of a process and see where do we spend the time? What methods consume the most number of CPU cycles? In this case, we had a bit of luck. There are several different parameters to perf, and it can behave in many different ways depending on the hardware. We are using Intel CPUs, and Intel has a register called LBR, Last Branch Record. So when you enable this feature, LBR stores the address of the latest branches in the code. And by sampling these registers often enough, you get a very accurate picture of where the time is spent, and without any significant slowdown also. For the other processors, this might not be as easy. The first column you see here, with the big red numbers, they are not as scary as they might seem. They are the aggregate number of CPU cycles or percentage of CPU cycles for a function. So it's the function and everything it calls. The second column is the percentage used by only that function. And since we had some knowledge of the implementation, we realized that this highlighted line with write slot, it's a low-level function that is called a lot of times and will consume quite a lot, but maybe not this much. There seemed to be something fishy about this one. But before jumping to conclusions, we wanted to run some other tests. We have an internal tool that is extremely simple. We have to all our APIs, to our different services, we write down timestamps when we enter the API and when we exit it, so that we can see which APIs take the longest. And when we did that, we noticed that one API took about 60 times longer than any other APIs. And of course, this was the API used for recalculating the switch fabric. So we were on the right track, at least. So that was good. Back to write slots. It doesn't really do that much, but it's called quite a lot of times. But looking at it, we found a call to something called verify switch present with a literal string, no switches present on the write slot. This looks like an error message, which it probably is. If we look at the verify switch present, we can see that it receives a standard string reference, and that seems a bit sane. I mean, we don't want to copy the string. Then we just check a member variable for the number of switches, and if we don't have anything, we throw an exception. Extremely simple. The reason for this one is that write slot is very close to the hardware, and we cannot be sure that the hardware exists all the time. We have full redundancy of all the different parts in the system. And if the FPGA responsible for the switch fabric, for some reason, have a problem, it could be in the middle of a failover to an alternate implementation. So what could be the problem with this one? Yes? Correct. You're perfectly right. Considering that write slot is called a lot of times, we could easily come up to 250,000 times for not even full reconfiguration. And using a standard string here, even though it's a reference here, we call the constructor with a literal string and copy the string into a standard string buffer. So this could be expensive. But since C++17, we have string view. This was a very simple change and kind of a no-brainer once you saw this problem. Unfortunately, we didn't run any more tests directly after this change. Instead, we started to look at the next thing to improve. GNU-perf is a really nice tool. You can see all these plus signs along the edge. You can click on these and expand these lines to see in all the different execution paths the time spent in the different methods. And there we could see that we call something called flush and then write cache. And of course, caches are used for many different things. In this case, it's also related to the hardware. If we write to hardware for every little change, it will take a really long time. So we need to buffer up several changes at once and write them all at the same time. The thing is that these changes, when we write when we empty the cache, that should be pretty much instantaneous, even though writing is slow. The writing is not seen in this output. So something's bad here. The basic idea of the function doesn't do much. We have a container having containing dirty slots. Dirty in this sense is that they have been changed by configuration and needs to be updated. And then we just go through this container and call the different subscribers of this information. And a set is probably good if you have a small change. But if you have a big change and you have to go through 6,000 slots, a set is probably not the best idea. Let's try with a vector instead. It's very fast to go through a vector and to see if to get in all the elements. But it could be slower for small changes. But anyway, we tried. The change is small, and we can always revert it if it doesn't work. So what happened? These two small changes gave us an improvement of almost 1 second for the large changes. And when we checked the API call to our service, we could see that for the small switch, it took 0.8 seconds. With a larger switch, 1.1. Now we're down to 0.5 seconds. That is 39% better than with a small switch. But we're still slower in overall performance for the whole system. So this is a good start. Hopefully we can do more. But first, we need to revisit this change between set and vector. Since when we checked the performance for the smaller channels, we could see that those got quite a lot worse. So we went back and compared just standard set and standard vector to see where do we get the best performance in what situations. And we could see we have a break-even point at 4,000 slots. And that corresponds to 2 gigabit per second. Now, this is a video switch. Everything we do concerns video channels. And updating a camera stream and you have 2 gigabit per second, that's pretty high resolution. Maybe not the highest, but it's pretty high. Many streams are smaller. So maybe we're not doing the right thing here. Now we brought in our product manager, product owner. We talked to customer support and more knowledge about our customers and how they configure the switches, the different use cases. But in the end, we realized that changing only one camera stream, that's a planned change. And if you do a planned change of a stream, you're probably not sending live data at the moment. So we don't care about those small changes. What we do care about is if someone breaks a fiber optics cable somewhere during a construction work or something else happens in the networks, we need to reroute traffic, then everything changes. So we need to plan for the worst case, the big changes. We talked earlier about write slot and verify switch presence. And I mentioned that we needed to protect ourselves from accessing hardware that might not be available all the time. And this goes for the whole API, for the whole class. And when we were looking at it, we could see that at times this might not be optimal. When we call write slot and then verify switch presence, and afterwards we call get type. But what does get type do? It calls verify switch presence, and that's not really good. So we needed to check, can we optimize this somehow? Can we get rid of this? And it turns out with minimal effort, we could just remove those calls. Fortunately, we didn't call those methods directly, so they should have been made private from the beginning, but things happen. Now we managed to cut down the reconfiguration time by another 0.4 seconds. So now we're faster than the small switch. That's a huge improvement. We did do some other things, but after these changes, pretty small changes, we didn't really find any good things to change, update based on the performance measurements. So now we started to change things basically at random. Instead of checking the container size inside the loop, we checked it before the loop. Instead of copying a list, we used a reference. We tried to improve cache locality, where we had a vector of 8-bit characters representing a Boolean, and changed that to a 64-bit integer, where each bit represented a Boolean. We didn't want to use a vector or bool because they are kind of weird. Did this help anything? Not really. We had a small measurable improvement, not really significant, and it wasn't worth the effort. But the conclusion from all this was we managed to cut down the time needed for a big reconfiguration with 66% with only these changes. And we're 13% shorter time than with a small switch. And we can also confirm what everyone else is saying. If you want to improve, measure everything. Measure before the change and after the change, because you don't know what effect it will actually have. And you need to measure several different use cases, because a change can improve one use case but make it worse for another. And focus on the logical changes. Trying to do the compiler's work is just a waste of time. You might make it a bit better at the moment, but in the long run, you might just make it harder to understand the code and harder to maintain it. Thank you. Any questions?